finally, in rotational motion, we're going to talk about angular momentum, which is represented by the capital letter L. Now, if you haven't done the momentum unit yet in Physics 30, you need to know what linear momentum is, which is just mass times velocity, okay? So it's kind of like an inertia of motion. So if something with mass has a speed, it has momentum. So it's just measuring something's inertia, how much inertia it has when it's moving, okay? So that's just linear momentum, anything with mass moving translationally. So of course, angular momentum is if something's rotating and moving. Then of course, if it has angular velocity, then it has angular momentum. Okay, so it is a vector, meaning we do care about direction. And with rotation, of course, directions we care about is usually clockwise or counterclockwise, not necessarily left, right, up, down, north, south, that sort of thing. Okay. So angular momentum, L, capital L is equal to I, which is of course rotational inertia, which is different for different bodies, but our typical equation for it is mr squared, which is just any one thing traveling in a circle about a center of mass that's not within that thing that's rotating. And then we're going to multiply that by its angular velocity. Okay. Now the direction of angular momentum and angular velocity are in the same direction. And how the heck are we going to determine the direction of angular velocity and angular momentum? We're going to use something called the right-hand rule. And so we're going to move our fingers in the direction of rotation. And that's, of course, for on our right hand. So, of course, if the direction of rotation is counterclockwise, we're going to spin our fingers around counterclockwise, and we'll see that our thumb is pointing up. If you spin your fingers clockwise in your right hand, then your thumb is pointing down. Your thumb is the direction of angular momentum and angular velocity. Okay, and so that is the direction of our angular momentum, angular velocity, L and omega. Okay, and if you're like, why is that the direction? Well, think about when you twist a screw or something like that. It's basically the same as the direction that the screw would travel in if it was turned in the direction of rotation. So if you turn a screw counterclockwise, it goes up, and if you turn it clockwise, it goes down. Okay, in that, the sort of orientation that it was showing right there on that page. But of course, then it could go forward or backward or up or down or anything like that, or left or right, depending on where the screw is, which way you're turning it in terms of where you are. And so that is how we know the direction of angular momentum and angular velocity. So it's just the direction that a screw would go if you turned it clockwise or counterclockwise. So we can relate this back to torque, because again, if we look at linear momentum and linear force equals mass times linear acceleration, this can also be written, Newton's second law, as force times time is equal to mass times velocity, okay? That is something that we cover in Physics 30, but again, does have to do with the fact that accelerations change in velocity over time. So in a similar way as that, we can express torque being rotational inertia times angular acceleration. And so we can actually take this, which we learned in rotational inertia, and we can write it in terms of angular momentum, okay? And so if we take a look at that and make, of course, since angular acceleration is change in angular velocity divided by time, and so we can rearrange that to get something like this, okay, where we have our torque equaling the change in angular momentum divided by time, which of course capital L, remember, is angular momentum. Okay, so if we're talking about just normal size things, we can use this. If we're talking something like where it has a massive, massive, massive radial distance compared to the object that is going around, then our angular momentum is just linear momentum times radial distance. So that's a whole different scenario. But for something that's not like that, where the thing that's rotating is so much smaller compared to the radius it's rotating at, then we're going to use this for torque, okay, and to find angular momentum. All right, let's talk a little bit about conservation of angular momentum. So, of course, there is such a thing as conservation of momentum. Again, we'll go over that in the Physics 30 unit. But what does it mean to have conservation of angular momentum? So, if there's no unbalanced external torque acting on the rotating system, then angular momentum of that system is constant, okay? So, this happens with linear momentum as well. So in the example of a collision or something like this, if there's nothing else acting except for those two things colliding, there's no external forces, then we have something called a conservation of momentum, where mass times velocity before is equal to mass times velocity afterwards. And the same thing is with angular momentum. Again, if there's no unbalanced external torque acting, just the stuff in the system acting on each other, that means that my angular momentum before, which is I times omega before, is equal to I times omega afterwards, okay? And so, of course, that is just if no external torque is at work. So let's go over a few examples of that, because what the heck does that mean? It just means nothing more than what's inside the system is making this thing spin, right? Because that's what the torque is. It's applying a force at a certain distance from a radial, from the center of rotation, okay? But of course, if there's no external torque being applied, then there should be a conservation of angular momentum. So a good example of this is a figure skater. So a figure skater can change not their angular momentum, but they can change their angular velocity by making their radius bigger or smaller. Now, this does not mean that they're changing their angular momentum, because as we know, as the rotational inertia goes down, angular velocity goes up. So that's why when you see ice skaters, when they start to spin faster, what do? They try to make themselves smaller. They try to make their radius smaller so they spin faster. But of course, as the rotational inertia I goes down, our rotational speed goes up, keeping our angular momentum exactly the same, right? Because say your angular momentum is, 10. Say you start with rotational inertia of 10 and rotational momentum or angular momentum of 1. Well, then what if we went up to, I went down to 5 and omega went up to 2? That would still equal to 10. What if I went down to 1 and omega went up to 10? That would still equal 10, right? There's a lot of ways to get 10. And therefore, by the ice skater bringing these arms and bringing them in, right, tucking them in, the ice skater can get a much, much larger rotational velocity, but then their rotational inertia goes down, keeping that rotational momentum exactly the same. Okay, so the rotational momentum at this point is equal to the rotational momentum at that point. Okay, so those should be both equal. So that's a good example of conservation of angular momentum, because again, there's no external torque. It's just the ice skater that's skating on the ice, that's rotating themselves on the ice, and they are applying the same torque, right? And all they're doing is changing their radius, which then changes the rotational inertia, which therefore changes their angular velocity. Okay, another example would be a person, say they're on a circular platform that can move. So at first, say they are standing at rest, then my angular momentum is equal to 0. So you're going to go, but what if they start moving? Then they have an angular momentum because they are moving. They have angular velocity and they have inertia. So what's going on there? Well, if this thing is allowed to move, then guess what? It's going to move backwards. This guy's going to move forwards, and it's just going to end up spinning on the same spot, okay? And if we follow our right-hand rule, we see, okay, well, this guy who's moving counterclockwise, of course, his angular momentum is going upwards, and then this thing, this platform that he's on that's moving clockwise is going to be, then his angular momentum is going to be going down. And guess what they add together to get? 0. So there's still conservation of angular momentum, where the angular momentum when he's at rest, which is 0, should equal to the angular momentum when he's walking on the platform and the platform is moving backwards and he's trying to move forwards and actually just staying in the same place but moving. And that's kind of like a really, really weird treadmill or something like that. I don't know. Now, of course, if the ground didn't move and it was just walking in a circle, then you have external torque from his legs. And then we don't have to consider conservation of angular momentum because then there's an external torque at work. Okay, so yet another example of angular momentum being conserved, where it's the same before as it is afterwards. Okay? Another example. This isn't one where it's conserved because it doesn't have to be conserved. Actually, no, it is conserved. What am I saying? Sorry. It's conserved because technically the torque on a planet is 0. Which way does the force of gravity act? Directly towards the sun. Okay? So stay with me for a minute. You're like, well, okay, what's going on? So the angular momentum of a planet is obviously the same here as it is there. That shouldn't be changing we shouldn't be changing our opinion on that, because we know as it gets closer to the sun, it's going faster. But it also kind of applies when you consider that planets at different distances also travel at different speeds, right? So when the distance between the planet and the sun decreases, of course, the planet's moment of inertia decreases as well, but then they're going faster. And that is why planets that are closer to the sun than the Earth go around the sun in a shorter time. Of course, we go around in 365.24 days, but planets that are closer go around in less than that. Planets that are further away, since they have a larger moment of inertia, go around slower than we do. So that is yet another example of conservation of angular momentum, because again, the only force that's at work is not a tangential force. Why does it keep going around? Just because it has already had that tangential velocity, because it has rotational inertia. That's why the planets are going around, because they have rotational inertia, but of course the force of gravity is going towards the sun. So there's no outside torque that is acting on these. So therefore the rotational momentum at that point should equal to the rotational momentum at this point, which is when it's closer to the sun. Just means it's traveling faster because it has a smaller moment of inertia. And there we go. So that is conservation of rotational momentum. So that's all I'm going to go over for now. It's going to be a little bit more difficult to do the math before you do the the conservation of momentum unit in Physics 30. So then I would go do that first and then worry about doing a lot of math with this one. But you can still try to do some simple stuff, because again, as long as we know rotational inertia at one point is equal to rotational inertia at another point, we should be able to figure out something. So say here I had rotational inertia of the figure skater here, rotational inertia of the figure skater there. Maybe I want to find out her angular momentum, how much faster she'd be going. right? Well, of course, I could find her change in angular, her moment of inertia. And then if we had her angular velocity at position 1, then we could find the angular velocity at position 2. Okay? And that's the end of rotational motion. So you know everything you got to know about rotational motion for physics AP. But of course, with this last unit, or this last little topic here with momentum, it will make even more sense once you go over momentum in Physics 30.